Hello, this video is going to focus on a particular function, and it's going to be a function that's going to be modeling accident rates. And the purpose of this entire exercise is to get accustomed to working with functions, function notation, function equations, and talking about our results in context. So there's a lot of stuff packed into here, but most of it should be stuff that we've talked about before. This video is just about putting everything together. So one of the first things that we need to learn how to do is how to read before we start doing stuff. A lot of times we'll start with reading part A and then looking up for context clues here to help us answer the question. Instead, you should read the question the way we read mathematics, and that is critically. For example, the function f of x equals, now you see all these numbers and stuff, but what I see is x squared, which reminds me of parabolas. I usually seem to get parabolas when I have these x squareds in it. So what is f of x trying to show me? It's trying to show me accidents. That's f of x is the number of accidents per 50 million miles driven. 50 million miles is a lot, so this is really just an accident rate, saying the average 20-year-old, if conceivably they were to drive 50 million miles, could anticipate 440 accidents. So it's just talking about how safe the drivers are. It says x represents the driver's age, and we go from 16 through 24. Now the age represents the x, which is the independent variable. The independent variable is associated with the domain of a function. So in part A, when I read state the domain of the function, I realize that they've actually just answered the question for me in the first sentence. All I have to do is acknowledge that I understand what domain means. Remember, domain is the set of numbers that are used in the input variable. That is the set of numbers that are acceptable for the x variable. So in this case, 16 through 74 is my domain, so I'm going to write it in math notation. X represents any age, 16 or older, or younger than 74, anything in between. And that's age in years. Then I just leave a quick sentence. It doesn't have to be a paragraph, it doesn't have to be a long involved thing. All I have to do is just write a sentence that says what I said in context and why it makes sense. So what I said here is the function only provides an accident rate for drivers from 16 to 74 years old. So drivers that drive illegally under the age of 16, this function doesn't qualify their situation. And drivers older than the age of 74, this function doesn't give appropriate accident rates either. That's not to mean that 80-year-olds don't drive cars. It just means that this function stops being reasonable by the time we get to the age 80. So that's the domain question. Now I get to part B, and it's asking me to determine the accident rate for 20-year-olds. 20 years is the age. Age represents the x. So what I'm looking for is, 20-year-olds means x is 20. I'm looking for f of 20. So most important in this is the notation, the skill notation that we're working with, and in this case we're talking about putting in wherever there was an x, we substitute a 20. So we need to square 20, multiply by 0.4, multiply 20 by 36, and subtract that, and then add 1,000 to the end. And so the rest is just sort of arithmetic, really. I asked you to do this without a calculator because number skills are something we need to develop. So many people would see the decimal and say, I can't do that without a calculator. But it's just 4 times 4, which is 16, and then you just have to figure in 160 is 40% of 400. That's the most reasonable. 16 is not 40%, and neither is 1,600, so 160 has to be right. Anyway, we take 160, add 280, and we have 440, and that's the answer. But in traditional class, we leave 440 and say that we did our work, but it doesn't mean anything until we put this 440 in context. So first I put a label down. The 440 is representing accidents per 50 million miles. And then I put in an English sentence, what does 440 accidents per 50 million miles mean? So what it means is the average 20-year-old should expect 440 accidents over a 15 million mile driving career. Essentially, it's just talking about how safe are 20-year-old drivers, and the whole point is we can now compare relative to other drivers. Now here what I did, it might be hard to see, but I went to Desmos and I entered in the function equation as given, and then I made a table of values based on that function equation so that I could actually see and label points on the graph. So I verified that 20-year-old drivers do indeed have an accident rate of 440 per 50 million miles. The rest of this is really straightforward. 45-year-old drivers, that's part C, so now I'm substituting 45 in for 20. I should anticipate 45-year-old drives being a little bit more safe, and that's what the math tells me. 190 accidents per 50 million miles driven. So basically, I want to point out my statement of understanding here. Some students will just write the same thing here that they did here and just say, all right, so the average 45-year-old could expect 190 accidents over 50 million miles. But I've already established that I understand what my accident rate means. I don't need to restate something that I already understand. So instead of actually restating my understanding, I'm going to add to my understanding. What is 190 telling me relative to what 440 told me? So to talk about it in context, 45-year-old drivers are more than twice as safe as 20-year-olds. So again, 45-year-olds aren't going to drive 50 million miles, and 20-year-olds aren't going to drive 50 million miles, but when we compare them in rate form, we understand the relative safety of 190 as opposed to 440. This also jives with common sense that as you get older, you take less risks, especially because you have kids and you don't want to die on them, and stuff like that. So that's why the 45-year-olds are a little bit safer. Notice again, I went back to Desmos, I added another value to my table and verified this. Now, if you actually look at all the different accident rates, it appears to me that 45-year-olds are in fact going to be the safest drivers of all. In a way, I cheated because we were supposed to try this without a calculator first, but when you look at part C, it's asking us to make a prediction as to what f of 55 would be. So would 55-year-olds be more safe or less safe? If you have a graph to look at, it should be abundantly clear that as we age past 45, we get a little bit less safe. We could even use common sense there without a graph to guess that the accident rate might be a little bit higher as people reach the golden years. So that's me talking and answering my question. I'm talking about it in context. Even though 50-year-old drivers are older, I suspect they'll have a higher accident rate than 45-year-olds. Again, my suspicion is based on a graph, but it's also based on common sense. To verify, then, I use my function notation, evaluate f of 55, and I find 230 accidents per 50 million miles driven. So indeed, 55-year-olds are a little bit less safe than 45-year-olds, as evidenced by the graph. And then I try to offer my explanation, and the whole purpose of this is to indicate that I'm thinking about what my answer means in the real world. So the reason why 55-year-olds must be less safe, it must have to do with the effects of aging. So eyesight's changing, reaction time's changing, whatever it is. So that's probably explaining why the accident rate started to increase after it had dipped initially. Last observations then. You'll notice, if you look at the work as a whole, you'll see that all of the work is organized in a way that's trying to make it easier for the reader. So we start working down the page, and then we go up to the next column, work down the page, and we go up to the next column, work down the page. You don't have in pencil usually very different color choices, but as you can see, the color makes it easier to read as well. So pay attention to this, like the flow of it. So I answer the question in math, and I translate it into English because there's a context here. I look at the given information, use it to answer the question in math, put in a context. Over and over and over again, we're going to keep seeing the same thing. We're trying to connect what we know about the world to how we use mathematics to describe that. So thanks for watching. Have yourselves a great day.